1-butanol. 1-butanol is a molecule made up of these pieces. 4 carbons, 10 hydrogens, 1 oxygen, put together like this. A more streamlined depiction looks a little like this, where each of the edges are carbon atoms, and the hydrogens coming off of those carbons are implied. 1-butanol occurs in several places in nature. It's an alarm pheromone in bees, so when a bee is injured, it will release some 1-butanol. And when other bees sense that, they'll become aggressive. Yeast, when they eat sugar, in addition to releasing drinking alcohol, also release a small amount of 1-butanol. And so when you do fermentation with yeast and sugar to create things like beer, whiskey, or wine, a little bit of 1-butanol is in all of those products. When you deep fry things, you also create a little bit of 1-butanol. And human beings use 1-butanol in a number of ways themselves. They use them in varnishes, those coatings that are used to protect wooden objects. They use them as plasticizers. Plastics can be firmer or softer. Firm like a medicine bottle, softer like this container, or even softer like a Ziploc bag. How soft the plastic is depends on how much of a molecule called a plasticizer you add to it when you're making it. There are many plasticizers. 1-butanol is one thing that those plasticizers can be. 1-butanol can also be used as a biofuel, and it's also used as an artificial flavoring agent in some butters and in some ice creams. Let's think about the safety of handling 1-butanol in the laboratory. The summary of a molecule's safety information can be depicted visually in these safety squares or fire diamonds. Let's look at these one at a time. Think about what each of these diamonds means. The blue diamond on the left represents how hazardous a molecule is to your health. It's just a description that's on a scale from 0 to 4, where 0 represents no health hazard and 4 represents a quick death on exposure. So 1-butanol is a 1 on that scale. That means it will irritate your eyes and skin if it comes into contact with them. At a higher concentration, it will irritate your respiratory pathway. And it could also have a depressant effect on your central nervous system, especially if you can smell it. And it has a sort of alcoholic smell, a sort of something between a harsh and a sweet smell to it. A more specific way to talk about the health effects of a molecule is to give a measurement called an LD50. A molecule will be poisonous to a different degree to different people in a population. Some people are more robust, some people are more frail. So the same dosage will kill some people and it won't kill others. You'll have a sort of normal distribution of how people are affected. The LD50 is the lethal dose for 50% of the population. This is the dose that would kill 50% of people if it were ingested. And for 1-butanol, at least as measured in rats, that would be at least 790 milligrams of 1-butanol per kilogram of body weight. The red square on the safety squares of this fire diamond stands for flammability. It's also on a scale from 0 to 4, where 0 is a molecule that won't burn at all, and 4 is a molecule that's a flammable gas at room temperature. 1-butanol is a 3, which is a significant fire risk. It has a flash point of 35 degrees or 90 degrees Celsius or 95 degrees Fahrenheit. The flash point is how much the molecule is able to evaporate to the point where if you are in a room with it and you light a match anywhere in that room, the air will burst into flames. So the flash point tells you the temperature you need for this molecule to be everywhere in the air, to have evaporated enough to be everywhere in the air, so that a match lighted anywhere in that room would turn it all into flames. And for 1-butanol, that's 35 degrees Celsius or 95 degrees Fahrenheit. The yellow diamond on the right tells you about the instability or reactivity of a molecule. It's also on a scale from 0 to 4, where 0 is a molecule that will not explode, and 4 is a molecule that can explode at room temperature. So 1-butanol has a 0, so it's not going to explode if you shake it around or if you pour it into water. The diamond at the bottom, the white diamond, represents sort of notes or details, and if it's left blank, then there are no special mentions. But notes that you could find there, for example, are if something's a strong acid or a strong base, or if something's radioactive. So here we don't have any special notes for this molecule, 1-butanol. Let's think about what 1-butanol looks like. We've already seen that skeletal structure. We've seen how that's an abbreviated, more streamlined way to depict this molecule here, this connection between those atom Legos. Let's take this 2-dimensional stick figure and turn it into 3 dimensions. We can see that here, get a sense of the 3-dimensional shape. And there's even another facet of this molecule that's being depicted with the colors, and that's the electrical charge, which ultimately tells you about the stickiness of a molecule. Chemistry can ultimately boil down to sticky shapes. Opposite charges attract, and so where there are charges, the molecule will stick to other molecules of opposite charges. Blue here represents a positive charge, red represents a negative charge, and green represents a neutral charge. This sort of depiction of the stickiness or the electricity on molecules is called an electrostatic potential map. Not only that, but the molecule doesn't stay still. Each single bond can rotate, and all bonds act like springs that vibrate back and forth. So here's a depiction of what that stick figure would look like in 3 dimensions as a dynamic, living thing. Now here, we've slowed it down enough so that we can see the twists, turns, and vibrations. But we are enormous creatures that live over epic timescales. To us, this molecule would be really moving much faster. Now here's what that molecule looks like if it's moving 20 times faster. Here's what it looks like if it's moving 400 times faster. But at room temperature, the real molecules that we would come into contact with would be moving around 2 trillion times faster than the original simulation that I played for you. So we are existing over these enormous timescales. So much can happen in the timescales that we exist over for molecules. Not only do we exist over enormous times, but we exist over enormous spaces. So in 1 drop of 1-butanol, you would have around 300 million trillion molecules. That's about the same number as the number of stars in 3 billion galaxies. That's in 1 drop of 1-butanol. And when you zoom out of those molecules and they merge together like pixels on a screen, what we end up seeing is a clear liquid. But now when you see that liquid, I want you to think of whole worlds that are existing over eons. Once the molecules come together, they can act in unique ways as a population. And those unique ways are called the physical properties of the molecule. So some physical properties of 1-butanol. First, let's talk about the freezing point and the boiling point when it transitions from a liquid to a solid or a liquid to a gas. For 1-butanol, the freezing point is negative 129.6 degrees Fahrenheit. The boiling point is 243.9 degrees Fahrenheit. Notice that those numbers are different than the numbers for water. Right? Water freezes at around 32 degrees Fahrenheit, and it boils at 212 degrees Fahrenheit. So 1-butanol tends to stay a liquid more than water does. And of course, as a scientist, you want to train your mind to be able to think in degrees Celsius also. So for comparison, the freezing point would be negative 89.8 degrees Celsius, and the boiling point would be 117.7 degrees Celsius. Another important physical property is density. Density determines whether something can sink or float, and so it creates structure in our world. Everything from separated peanut butter to the layers in the crust, core, and mantle of our Earth. All those layers, all that structure is determined by density. So the density of a molecule will determine where it goes in different regions in our world. And so for 1-butanol, the density is 0.81 grams per milliliter. This is telling you how much stuff you have in a certain space. A milliliter is about the volume of the end of your pinky, from the last joint in your pinky to the tip of your pinky. That's around 1 milliliter. And so that would weigh around 0.81 grams for 1-butanol. For comparison, the density of water is 1 gram per milliliter. And so water is more dense. What that means is that water is going to sink, and 1-butanol would float on top of it, and you would get these different layers, just as you can see in this example graduated cylinder on the left here. So 1-butanol would float on top of water. But at the interface, some of it would dissolve. Another way that you can create structure in our world besides density is solubility in water, and for us that's especially significant at room temperature, the temperature that we do a lot of experiments. How much does 1-butanol dissolve in water? Solubility ultimately depends on the electricity in a molecule. I have 1-butanol on the left here and water on the right. The rule for solubility is that electrical charges come together and neutral molecules come together. So a neutral molecule will combine with other neutral molecules, an electrical molecule will combine with other electrical molecules, but the two will stay apart. The electric charges will stick to each other and they'll exclude the neutral charges. That's, for example, why oil doesn't mix with water. Water is a very electrical molecule. It has a lot of charges on it. That will want to mix with one end of 1-butanol, but it won't want to mix with the other. So 1-butanol is only slightly soluble in water. It will only mix a little bit. It'll mix around 73 grams per liter at room temperature. So 73 grams would be about enough to hold in your palm, and a liter is the size of a salt container at the grocery store. Finally, how can you make 1-butanol? How is it made in our world? As with a lot of carbon molecules, you can make it from the oil that people drill out of the ground, petroleum or fossil fuels. Those are ultimately liquid fossils. They are the decayed corpses of the forests of ancient ecosystems that were buried over time, and all of that plant matter gets degraded. Everything that those plants made out of carbon dioxide gets broken down and crushed up, and you get these black fluids, these mixtures of a bunch of carbon molecules. You can take those mixtures and you can separate the stuff in them by doing a process called distillation. Basically, distillation is how rainwater works and also what happens when you boil spaghetti. So, rainwater is not salty. You separate the water from the salt in the ocean because the water evaporates more easily than the salt does. In a similar way, with distillation, you can take a mixture of things, like those fossil fuels, heat it up only a little bit, so some things evaporate but others don't. Oops. And then that, just like the rain condenses and falls back down, you could have those vapors condense and drip back down into another container. And so you could separate all the different molecules that are in petroleum using this process of distillation. Doing distillation, you could get this molecule here at this top left. It's called propylene. And if you mix propylene with carbon monoxide, it comes out of car exhaust, and hydrogen gas that used to be used in stoves, you can end up getting this next molecule here. And if you combine that molecule with a little more hydrogen, like is used in stoves, then you end up getting 1-butanol. So that is a little background on 1-butanol.